Hello and welcome back to another video podcast from Podcast School. Today we're going to be looking at electronic systems, and this is the first of two parts, and this is all about logic. Okay, so in GCSE Technology and Design you may have met logic circuits before. This stuff, if you like, is the real basic, the real bare bones of logic, and will be the real core foundation of the stuff that we'll do over the next wee while. Also, when we come to do A2, this stuff will be second nature by then. Okay, so let's have a look. We've got an LED, and we've got attached to it two switches, A and B, and I'm almost certain you would know when this LED would light. But we'll go through it anyway. We've closed A, and of course Q does not light. And you've guessed it, in order for Q to light, the LED to light, B must also close. Okay, so there we go. Yeah, so B is now closed, and of course the LED lights. And notice I've got this thing on the right hand side called a truth table. 1 means basically the switch is closed, and 0 means that it's open. So for initially, whenever I closed A and B was open, well then Q was not on, or 0. Okay, but now in this state, when A is 1 and B is 1, then Q obviously is a 1, it's on. And just to fill out the table, I've said that when A is open, although I haven't showed it here, when A is open and B is a 1, then of course Q will be off again. Okay, now that's a truth table. It's an AND truth table. It says that A and B must be 1 in order for Q to be 1. That's the only time, you'll note that that's the only time that Q is a 1, when A and B is a 1. All other times, Q is a 0. And that makes sense if you think about it in the terms of this little circuit here. The only other thing to note is that the symbol for an AND gate is this, well, I don't know really how to describe it. It's a rectangle with a round end, I guess. The inputs are on the left, and the output Q is on the right. Okay, that's an AND gate. Now, when we want to use an AND gate, we simply get it from a chip. And normally chips that we use in school have 4 AND gates in them, and you can see that the pin output is given here. So if you look at this top left one, the inputs to this logic gate, this AND gate, is in pin 1 and pin 2. Pin 3 is the output, and so forth and so on. You can see as you go around the circuit, you can find the output of the other 3 AND gates within that circuit. I'll just say, just very quickly, that as I've written here, it says it's important to realize that logic circuits or logic gates, including the AND gate, are implemented using transistors. They're all transistors. In fact, transistors is like the basic building block to all electronics. Just much in the same way living things are made of cells, transistors make electronics. So don't be thinking that this is like a little piece of magic that just happens. It's not. They're all based on transistors, and this symbol is the simplified symbol, or a simplified way of writing a bunch of AND gates. Okay, well, I don't want to get too bogged down in that, but I just want you to make you realize that we're thinking about, when we talk about logic gates, we're really talking about transistors in a particular setup in a particular way. Okay, so let's move on to the NAND then. The NAND is the direct opposite of the AND. Okay, so if you're thinking about a NAND gate, just think of the truth table for an and really it's whatever Q wasn't in the AND truth table. So a 0 and a 1 will give you a 1, a 1 and a 1 gives you a 0, and a 1 and a 0 will also give you a 1. Okay, so in the AND truth table, there was a 0 here, a 0 here, a 1 there, and a 0 there. So this is almost just the inverse, okay? And that's a NAND gate, and you denote a NAND gate by a little circle on the output. Again, if you're going to use these in school, then you will receive a little integrated circuit here, or an IC, and that would be the pinout for it. Okay, I've asked a question here. I've said derive the truth table for a NAND gate whose inputs A and B are connected together. Okay, let's take a look down in this these truth tables. Okay, there's 0 and 1, and I've grayed that out because, well, if they're tied together, if A and B are tied together, then obviously A can't be different from B. So that 0, 1 in the truth table doesn't make sense. This one does though, a 1 and a 1, and you know that earlier for a NAND output there will give you a 0. Okay, again the lower one doesn't make sense because A and B are tied together, so they can't be different, so we don't even consider that. But look at the two that we do consider. 0, 0, or in other words, one input 0 gives you an output Q of 1. An input 1 gives you an output of 0. Okay, so or the simplified table looks like this. 0 gives you 1, 1 gives you a 0. In fact, this is an inverter or a NOT gate. It inverts the input, and it's got its own special symbol. Okay, it's a triangle with a circle on the end. Now, I've said derive the truth table for the combinational logic. That should really say below. Okay, so you've got two NANDs, one whose inputs are not tied together and one whose inputs are. Okay, if you think about this just before we start, I think you should be able to get the answer. We've got a NAND here, and we've got a NAND here whose inputs are tied together. We've just seen that's an inverter. So a NAND inverted, if you're thinking very carefully, should give you an AND, back to an AND again. Okay, let's check that out. And indeed, yes, it does. Okay, there's the truth table. If you wanted to really think about that through completely logically, what you would do is just put an extra column in your table and maybe write a little C in here and then call that column C, and then work out what all the C's would be given the inputs A and B, and then of course Q would be the inverse of C, and that will give you that output. Okay. Now this is the OR gate, and this is the symbol for an OR gate, and to show you and to explain it a little bit, I've drawn this circuit diagram again with the LED. This time our switches are not in series, they're in parallel. We've got A and B together, and I think you can see this right away. If either one of these switches is pressed or switched, then the LED will light. Okay, and let's fill out our truth table. So 0 and a 0, so open will give you no output at Q. A 0 and a 1 though will give you an output at Q. A 1 and a 1 of course will, because there's two ways for the current to flow, and a 1 and a 0 will give you a 1 also. Okay, so all the outputs at Q will be 1, apart from when neither switch is switched or on. In other words, to put it another way, Q will be a 1 when A or B is a 1. Okay, that's the OR gate. Again, there's the symbol, or sorry, not the symbol, the pinout for an OR gate if we're using this in school. Alright, and you've already guessed it, a NOR is the direct opposite. Just the way the NAND was the opposite of an AND, the NOR is the opposite output of Q for an OR. Now, this is a really, really tricky question. I've said the question is, using only NAND gates, construct a NOR gate. And I know I've asked that in the past before, and I'm not quite sure if anyone's ever got it, so it's a really, really tough question. It's one of those ones that you would probably pore over for a long time. What I would say is, you would not be asked that in an exam, of course not, but what you might be given is the circuit diagram. Okay, and that these NAND gates tied in this way should give us a NOR, and I'm going to just show you how you would check that out. Okay, I've put in extra symbols here, C, D and Y. Okay, so in an exam, say you were given this and maybe the inputs were labelled A and B and the output was a Q, they may not put in anything here, so there may not be a C here, there may not be a D here, and there probably wouldn't be a Y there. but you put that in, okay? You can label these any way you like. This doesn't have to be C or D. I usually put C or D because it follows on from A and B, obviously. But then on the output side, I normally just go back one, make it a Y or a Z or an X, up to you. Okay, so the best way to do it is just follow it through. Remember that your inputs, A and B, you should always label them like this. So A, 0, B, 0, A then 0, B then 1, A then 1, B then 1, A then 1, then B then 0. So it should read 0, 0, 0, 1, 1, 1, 1, 0. Sometimes people say that, well, you know, why not put this down as 0, 0, 0, 1, 1, 0, 1, 1. And that's not a proper way to do things. This is the proper way to do things, to have 1 and a 1 after here, because I'll tell you why. In each case, to get from one row to the next, only one input needs changed. If I made that third row begin with a 1 and a 0, then A needs to change to get from a 0 to a 1, but B would also need to change to get from a 1 to a 0. So that's not good practice. So keep it as 0, 1, 1, 1. That means that only A changes between these two rows. And again, B changes between the third and the fourth row. Okay? So let's fill out this table. C then, with the 0 and a 0. Remember, these are NANDs and they're tied together, so they're inverted. So C is just the opposite of A. Okay, D is the opposite of B, and Y is just the NAND function of both C and D. Okay, so 1 and 1 there will give you a 0. Remember, these are inversions of A and B. So 1 will, because of inputs C and D being 1 and 0. 0 and 0 gives you a 1, and 0 and a 1 will give you a 1. Okay, then Q is just the opposite of that. Okay, 0, 0, or 1, 0, 1, 0, 1, 0. Okay, so look, the output Q there is the same as here, and this is the NOR truth table. So in fact, this is a NOR gate. A very complicated NOR gate, but a NOR gate nonetheless. Okay, we're nearly there for this one. Just one last thing to say. This is an exclusive OR gate, and you can denote that by a little line. So it's the same as an OR, but with a line. And look at its truth table. 0, 1 gives you a 1 as before. A 1 and a 1 this time, look, gives you a 0. That's the change. And a 1 and a 0 this time will give you a 1. So it's the same as an OR gate, only except to say that a 1 and a 1 gives you a 0. That's the change, that's the difference. That's why this is an exclusive OR. And you've got it. An exclusive NOR then is well, let's just fill out the table. So a 0, 1 gives you a 0. A 1 and a 1 will give you a 1. And a 1 and a 0 gives you a 0. So it's just the opposite of an exclusive OR. Whew, that was a lot of information there, and hopefully not too long a time, 13 minutes so far. Try to get these finished definitely before 15 minutes. That's it for now. That's just all the facts that you need to know. Next video podcast, we'll take a look at some questions involving this stuff. But for now, thankfully, that is it. See you next time. Bye-bye.